Hello everyone, I'm Dr. Siddheshwar Chopra and we'll be starting today some very important concepts of a new module which is called the relativistic mechanics. Introduction. At the beginning of the 20th century, it was found that the classical or Newtonian laws of physics were inadequate to explain the various phenomena at microscopic level or in cases of bodies moving close to the speed of light. Albert Einstein developed the special theory of relativity, here now abbreviated as STOR, in the year 1905. Here in STOR, the gravitational effects and accelerated motions are not considered. Here, the absoluteness of mass, time and length were discarded, and it was theorized that these quantities depend on the frames of reference. So what is relativistic mechanics? Very simple definition is it is the branch of mechanics dealing with the relative motion of bodies. So now getting to the very important concept which will be used in every lecture from here on, it is called frame of reference. So it is important to keep in the back of your mind that measurements made in one inertial frame, we'll be discussing what are inertial frames shortly. Measurements made in one inertial frame can be transformed to measurements in another frame by Galilean transformation equations in Newtonian physics. So wherein we are talking about velocities much lesser than the velocity of light, c, and the Lorentz transformation equations in special theory of relativity. Therein we have a velocity almost of the order of velocity of light. So any physical event or parameter is measured with respect to a well-defined coordinate system, which is nothing but a space-time coordinate system or object called frame of reference. What are the kinds of frame of reference? There are two main categories of frame of reference. One are called inertial or accelerated frames of reference. Other ones are called non-inertial or unaccelerated, non-inertial or accelerated frames of reference. Now we understand what are inertial frames of reference. These are the frames in which the law of inertia or the Newton's first law holds good. All the inertial frames are in a state of constant motion with respect to each other and hence do not accelerate. Earth is assumed to be an inertial frame of reference. Please remember, it is assumed to be inertial frame of reference. What are non-inertial frames of reference? Yes, these are the frames that accelerate with respect to an inertial frame. Basically, these are the frames which do not move with a constant velocity. Velocity is continuously changing. Okay. Hence are also called accelerated frames of reference. So any jerky motion of any body can be taken as a non-inertial frame of reference. So this does not form the part of discussion in STOR. So we'll be continuously focusing only on the inertial frames of reference. So let us start with the classical set of equations, which are very simple to understand even. The classical set of equations are called Galilean transformation equations, which relate the space and time coordinates of two frames of reference. Here we are again talking about inertial frames of reference. So let us define a system such that S dash be an inertial frame of reference moving with respect to another inertial frame of reference S, which is at rest. This is your S frame of reference on the left hand side in the diagram. Right hand side is your S dash frame with a constant velocity v such that v is far less than c along the positive x direction, and both s and s dash coincide with each other at t equal to 0. Two observer O and O dash are at the origin of s and s dash respectively. Let a point P in space-time, or we can also call it an event, in the frame S dash. Here you can see P point has been plotted. This is some event which has the coordinates x, y, z, t with respect to S frame, and x dash, y dash, z dash, t dash in S dash frame as measured by observer O dash. Okay, so the prime quantities are the measurements with respect to observer O dash in frame S dash, and unprimed quantities are x, y, z, t. These are the measurements with respect to observer O in frame S. So it's very simple to see from the diagram itself that these classically the relation between the coordinates of event P in S and S dash will be t dash is equal to t, because the velocity is so small compared to the velocity of light. T dash is equal to t, which can also be written as dt dash is equal to dt. So we can also call this that time is absolute in classical physics, or even the time interval between any two events is also invariant under Galilean transformation. So classically it was believed that time is absolute. Okay, so if you have any two events, say we are talking about events p1 and p2, then we can also say that t2 minus t1 is equal to t2 dash minus t1 dash. So that is what is meant by time is absolute, or even the simultaneity of events holds good. Similarly, we can get other equations which are x dash is equal to x minus vt. From the diagram you can see this is your x dash and this is your x, and after a time t, moving with velocity v, now the distance traveled is basically vt. Okay, so you have x dash is equal to x minus vt. That is very easily visible from the diagram. So again, if we differentiate both the sides with respect to time, we will have dx dash by dt dash is equal to dx by dt minus v. What is dx dash by dt dash? It is u dash. And what is dx by dt? That is u. So you see u dash is equal to u minus v. This is a very important relation. You have to understand this. Now y dash is equal to y, which implies dy dash by dt dash is equal to dy by dt. Similarly, z dash is equal to z, which implies dz dash by dt dash is equal to dz by dt. This result is coming into picture because we have taken motion only along x-axis. So we'll be continuing further. It's very important to understand the notations or the terminology used in this module, wherein I've written it as note here, equations with primed quantities which are x dash, y dash, z dash, t dash on the left hand side. If these quantities appear on the left hand side, then these equations are termed as direct equations. So you can call it direct Galilean transformation equations. If if x, y, z, t, the unprimed quantities appear on the left hand side, these are called inverse equations or inverse Galilean transformation equations in this case. So primed on the left hand side are called direct, unprimed on the left hand side are called inverse. But please remember, if primed quantities are on the left hand side, then only the unprimed quantities will be available on the right hand side. So there should be no mixing of primed and unprimed. How do you get these equations? How do you convert? So converting from direct to inverse equations is very easy. To obtain inverse equations, you can just change change primed quantities to unprimed quantities. We'll be seeing from the previous equation. Uh, x dash can be changed to x, y dash can be changed to y, z dash can be changed to z, t dash can be changed to t, and v has to be replaced with minus v here. So if you see in the previous equation, in the previous slide, here you have x dash equal to x minus vt. So if I were to change, these are the direct equations I have obtained. If I need inverse equations, I will have to change prime to unprimed. So this on the left hand side becomes x, right hand side it becomes x dash, and t becomes t dash, but v becomes minus v. So herein you have uh, this equation. You see here, t becomes t dash, x becomes x dash plus vt dash, because v has been changed to minus v. So x dash plus vt dash, y equal to y dash, z equal to z dash. These are your inverse Galilean transformation equations. So even if you have derived the direct equations, you can get back to the inverse equations if needed using this concept. What are the key points from the Galilean transformation equations. Newton's law of motion are valid in every inertial frame. These are seen from these very simple relation classical equations, all the Galilean equations. You can see the laws of physics, laws of motion remain same for every inertial frame. Now from the second result, u dash is equal to u minus v, or if we have u to be equal to c, then basically if we are talking about the photons here, I should say, so we are having c dash is equal to c minus v from the result of the Galilean transformation equation, which says that second postulate of STOR is violated. We'll be learning what are the special theory of relativity postulates in the next slide. So wherein we get to the postulates of special theory of relativity. These postulates were given by Einstein, and these are very, very important, and these are the pillar for our special theory of relativity. The first postulate is the principle of equivalence, which says that all the fundamental laws of physics must remain same in all the inertial frames of reference. If the laws of physics were different, then it will be very difficult to discuss any such systems at all. So laws of physics have to be same. There has to be some common platform with respect to which you can discuss the special theory of relativity, isn't it? So the second postulate is the principle of constancy of the speed of light. The speed of light in free space has the same value. What is that value? 3 into 10 to the power 8 meter per second in all inertial frames of reference, independent of the speed of the observer or that of the source emitting the light. If you see here, we can also call it, we can also write as c dash is equal to c. So the measurement of speed of light with respect to observer in s dash frame should be equal to the measurement of speed of light by the observer O in frame S. So that is what the second postulate of special theory of relativity says, which has been violated here by the Galilean transformation equations, wherein you have C dash is equal to C minus V. So this is a very important result from the Galilean transformation equations. So that's all for today. Thank you everyone.